Thank you very much. I plan to speak for 30 minutes. That's sort of at least the plan. So first, when we talk about uranium, I just want to give you a slide, just some very fundamentals, because you might ask yourself, what's the product of a uranium mine, and how that has been used, and what's the fuel cycle in it. So on the left, so we start out with a mine, and that's the product of any uranium mine there is on the planet. It's yellow. It's called yellow cake. Simply, it's a uranium oxide. Tends to have a yellowish color, hence the name. That isn't fuel yet. What needs to happen then is a conversion, and it will be converted to UF6, uranium hexafluoride. And the beauty of that is above 55 degrees, it's a gas. In this cylinder here, that's sort of the condensed version of it. Once it's converted, it needs to go into the enrichment. And the reason for that is that natural uranium has two isotopes, 238 and 235, and natural uranium, about 0.72% is that 235 uranium, which is the source of energy we use in nuclear power plants. And in these centrifuges, that gets enriched to about 3 to 5% to be used in sort of the most common nuclear power plants. And that material goes into a fuel assembly and get used. So there's after the mine product, there's quite a bit of a supply chain which needs to go through. But enough of that. Let's look to some basics of isotopes. And I'll point out the important bits. Don't need to try to read everything. The important bits are that we got, for those two uranium isotopes, we got two decay chains. And the 238 uranium decays at the end to the 206 lead, and the 235 to the 207 lead. And nature gives us this fantastic isotope system that we can use to date rocks. Two different independent decay chains, but they're identical elements. So it fits together in the same minerals. And that's where that fantastic geochronometer comes from. Now, when you go out and when you look at movies, TV shows, and you go as a geologist out in the field, you tend to see, or you use a Geiger Muller counter or a scintillometer, and you hear it ticking away or gives you numbers on the display. What you're detecting with those is not the uranium. It is 214 lead and 214 bismuth down here. Those two isotopes are the main gamma emitters, and that's what we're detecting with our instruments. That has very practical implications. If you're looking at very young uranium deposits, say formed in the last few million years, and you have interaction of groundwater, uranium is very easy to mobilize. Some of the other products in here are not. They're very relatively immobile. Like if you somewhere a thorium isotope in here as well, that will just sit there, will not move, but uranium moves. So you have examples where you think you have a great uranium mineralization, and then you take a sample, send it to the lab, and there's not much uranium in it actually, because the uranium was moved downstream somewhere. Just something practical to keep in mind. Now to the Damara origin, Namibia. This globe is upside down to our current view of the world. So north is down here. There's West Australia, Antarctica, and on the other side the Congo Craton, and the Kalahari to the south. And that ocean in between, the Comoros Ocean, closed up at about 570 million years, starting to close that ocean. And in between, that's where the Damara origin is situated today. And that's where the location where we look at the geology. Now, again, that's sort of a normal view, what we used to. Congo crater on top, Kalahari crater at the south with this Archean Zimbabwe and the Cabral crater. And here in between, that's a Damara belt. So it belongs to the system of Pan-African origins across Africa and elsewhere, across the Gondwana. A little bit moving down the scale. And again, Congo to the top, Kalahari to the south. And in between, we have this origin. It consists mainly of Neoproterozoic sediments, 800, 700, 600 million years old. They're very, very little volcanics. In fact, the only remnants of the old oceanic crust of a basalt, it's called a matchless belt. This is a little, in Google Earth, you can follow that very easily. That tends to be 200-300 meters in thickness, and that's all there is of basalt in this whole origin. Peak metamorphosis was around 510 to 500 million years, and I'll show you a map, sort of overlaying, sort of in these areas to the south and to the north, so the north zone and the south zone. That is sort of more typical medium temperature, high pressure metamorphic assemblages, whereas in the central bit in here, that's granulite phases 800 at 4 or 5 kilobars, so not very deep but very hot. And you have intensive intrusive magmatism starting 570 all the way to 500 million years. And it changes, the character changes from a more calc-alkaline to a S-type leucogranite, very poor in mafic minerals in them. So just a quick cross-section to get you the eye in. So looking towards the ocean. And the important bits are here, sort of these lineaments here. And where I'm going to talk about is this southern central zone. And that is the area where you, if not all, but the vast majority of uranium mineralization deposits, mines are located. So we're sitting in this very hot part of the origin. Now, to the uranium mineralization. I want to draw your attention to the map first. So we're about 50 kilometers to 70 kilometers east inland from Swakopmund. Swakopmund is a local town at the coast, Atlantic coast. One thing it probably points out, these are all deposits. There's the Ressing mine. There would be the big Ressing SH pit. There are other Ressing ore bodies, or say deposits, which haven't been mined simply because of more complicated mineralogy. And there's one more bigger project up here in Valencia. Otherwise, they're all following sort of a corridor along here, very prominent. You can see here probably the Husab mine, some workings. That opened in 2014. So it's active now, it's been mined. Ressing still get mined. Ressing opened in the 1970s, so producing over 45 million years. They produced about 320 million pounds of uranium in the time. Value-wise, that's comparable with a 10 million ounce gold deposit. And I just, if you're interested, the uranium mined in that over that time could power Australia for about 25 years. So it just sort of gives you an idea how much energy is in such a mine. Now to the uranium idea. So the current model goes back to Paul Nex's work and his supervisors at WITS. He did his PhD back in the late 90s, early 2000s. He worked in an area sort of just slightly off the map here. He found there are 6 distinct types of leucogranites, and this distinction has been all made based on field description, how they are arranged to their host rocks. Are they deformed? Are they folded? Are they boudinaged? Are they cross-cutting? Are they straight? These kind of relationships were taking account to devise 6 different types of leucogranites. And that model basically has been followed by all subsequent workers. naturally, they all have a bit of a different uranium-thorium ratio, and there's also some slight difference in rubidium strontium ratio and other little elements. That model says it's a really magmatic system, and no major fluids are involved. And the conundrum, and that was all stated in various publications, is that only number 4, the 4th of these leucogranite intrusions is uranium rich. And it was also noted that that one is following restricted to the Kahn resin formation. And what you see here, it's sort of along that there seems to be a stratigraphic control on the occurrence of these uranium-rich leucogranites. So that's the established view of that part of the world. Now, I don't want you to read through the detail, but that's sort of the rough stratigraphy. The main thing to point out, where most of the uranium deposits and mines occur stratigraphically, is in here. There's some more up here, but the vast majority sits between the Kahn formation, which is predominantly pyroxene, amphibole-rich gneisses, tending into being amphibolites. And at the top, you have the resin formation, and it's very variable. You have lots of marbles, biotite schists, some minor quartzites, very smaller units, including calc-silicate rocks, very heterogeneous. And I'll come back to that point. One thing we also need to include is there's always talk about the adaptive basement, and I won't dive into that because that's another talk. But the established view is that this basement is older than the Damara. And we had a PhD, we supported a PhD student, and he looked into that, how that relationship is. And I got one diagram from his studies, and so the blue is the basement underneath here, and from the Nozick group, that's all of that together. There's some compilation of studies of the diagonal zircons. We look at that and say, well, we think they're the same. So with other observations, so we would include all of that together. It's just a continuation lower in the stratigraphy. There's no pre-Damara basin to what we think there is. But now back to those two units in here. That's a study Foster et al. 2015. He looked at the hafnium isotopes of zircons and looked at the nature of these in terms of where they come from. Are they being shattered, these sediments, from the northern Congo craton or from the southern Kalahari craton? And also whether the material is more from a depleted mantle or from crustal recycling. And the interesting thing is that these rocks at the bottom of this stratigraphy is mainly recycled material, crustal recycling from the Congo craton, so from the north. And that has an aspect of our source region, because that material is rich in uranium, thorium, and potassium, very potassium rich. And all these elements will mean you heat up the crust, and that is an explanation for the high temperature metamorphism. So it creates the heat, and with that, the partial melting of the crust, generating these enormous amounts of granites. Now, we'll zoom a little bit further in. So that's just a map. So that border is one of our tenements. The blue outline is a marble horizon. So that would be equivalent to a resin formation. And outside around here, so the dark is the Kahn formation. You see there's dark slivers everywhere here. So this is our host lithology. And into that host lithology, we have all the leucogranites intruding. Everything which is sort of these white rocks in here, they're all these leucogranites. Needless, that's uranium channel from an airborne survey. Needless to say, not everything is mineralized. Would be too easy then. So there seem to be vast amounts of granites are not mineralized at all. So that's something to keep in mind. So it's, and when you go into the field there, and I'm showing some pictures from the field, it's really you're amazed how similar all these rocks look like. You can walk a transect here and sort of to your eye, and when you look in closely, they appear very similar, and you would get to the conclusion they're all fairly much the same event. And if you look at age dating throughout the whole belt, they all come back very consistent with ages as well, but not all of them are mineralized. Now, I'll go back to that. So that image in the two slides are taken from around here, looking to the northeast. So here you can have an impression. The intrusion patterns are rather random, not completely random. There tends to be a predominantly pattern. So for example, here, sort of dipping to the west, you can see there's a big end. We're looking essentially into an anticline, and on this limb here, it's dipping into the east. It's just sort of, so I'm gonna, in the next few slides, I'm going to go through a system of source region, pathways, and deposition sites to explain how we think this mineral system of these uranium deposits, this uranium mineralization, came about. And the most important concept to understand there is, when we go out in the field and look at the outcrops, is the rheological contrast. How they interact between the melts of these felsic intrusives and the various host rocks. And I'll show you a few pictures. So in this image, the host rock here is a marble, and into that marble intruded a leucogranite. And sort of intrudes here, and then it's sort of gobbled up a bit, and then the rest of this granite is over here. And you can go all the way along, and you see that it intrudes syn deformational. It gets the marbles deform further, and you have this translocation of parts of this granite dike, but internally you don't see much of deformation. And the reason is that marble, of course, can take up the strain so much more easily, and we need to remember it's 800 degrees hot, than a felsic magmatic rock. So it's much more rigid. Another example is over here. So there's a bit of an amphibolite in here, sandwiched in between a biotite schist. And while, especially on this side, you don't see much of veining, but in here you see these necks, so the incipient of a boudinage starting here. And in these necks of these boudinages, you have carbonates in here. So dissolved from elsewhere, from the marbles that are nearby, and you can see that these more rigid, more brittle acting amphibolite layers reacting differently to your biotite schist. And one more picture. So this is again marbles here, bottom and top, and in between you had a layer of pyroxene, amphibole gneiss, calc-silicates in there, much more rigid, can't take the strain off, it breaks up, it boudinage, and it's a very nice example. And then the marbles sort of taking all the strain up here. And you can see a lot of isocline folding in there, and all these kinds of observation. So it really makes, it's really important to keep it in mind, if you have a wide variety of lithologies, how they react at those metamorphic conditions. Now, when we look at, I talked before about why we think that's uranium-rich stratigraphy. It's because we have all these highly evolved crustal material, sediments, very little volcanics in that pile, which, due to the metamorphism, started to melt. And now is the question, how do we move that into the depositional sites? So this is just a magnetic map, and I sort of highlighted the marble horizons around here. And these are 3 of our deposits there, so Angola, MS7, and Inca. And you might spot that they tend to occur in these fault hinges. And that is in fact not a coincidence. Mostly the leucocranites, as I showed you before, they are everywhere. So you can find leucocranites all across along here, but they're not actually all mineralized. Mineralization tends to be focused in these fault hinge areas here and there. And what you can observe when you look at how the deformation style changes, you go along this area here is sort of all S-tectonitides, are very flat applied features. You go into these fault hinges, you see outcrops, basically pencils sticking out of the ground. So it's all lineations in the tide faults. Now we move on to what are these leucocranites mineralization actually look like. So this is just an image close up of one of these. This is a collection of about 350 samples across not just our ground, also various samples from other deposits and areas across the region. They tend to be fairly consistent in its major element composition. And that continues even if you look at things like rubidium, cesium, they are not extremely enriched. So you won't find rubidium values in the thousands of ppm. You're talking about hundreds of ppm. So they are not extremely fractionated. The interesting thing is, however, is this bit down here. And we get samples that close to 90% of SiO2. And when you're out in the field, so this is a mineralized outcrop. And in here, it's sort of this, I call it vein, or maybe someone can call it just an accumulation. That's one observation. The other one, you can see patches of pegmatites where all of a sudden your grain size is vastly bigger. And these, in chord, it looks like that. So very heterogeneous. So it's not very homogeneous. So you come from a sort of fine medium grain to all of a sudden you have these big feldspars in here. You can see them here. Then you have in the section where it's basically full of quartz. And all these features are pointing to a separation from your fluid phase from your melt. So you're starting to have a magma which is slowly solidifying. So you get your first crystals of feldspars, and then also you're starting to have your fluid separate to that. And that's what we're looking at. Very similar what you can observe in tin granites, in copper porphyry. So all these signs that you're separating your fluid from your magma. And we'll look now a little bit closer. So this is a N-cube half core. At the bottom, that's a micro XRF scan, uranium. There's the edge of what we call the quartz vein. It's about here. Most of the red areas, that is uraninite. So there's a little bit in here, but not too much. You might observe these fractures. And these fractures are secondary uranium minerals, uranophane or bolbodite. So they are uranyl minerals, which happen quite a bit later. But the key point here is most of the uranium is concentrated in this part and not so much in this part. Now this is a phase-matched image of the same sample, of the same scan. So there's mainly a lot of quartz. The orange is K-feldspar, and the pale green is plagioclase. And I think it's mainly albidic plagioclase. And the other thing you can observe is when you look closely, you see that the plagioclase sort of forms a network around the grains of the K-feldspars. And that's a typical thing you can observe everywhere in granites. You have a late albedoization, and it's that these intrusions, of course, they're pulses of intrusions. It's not everything at the same time. So the later ones, when they shed at greater depths, they're fluid. They will then cause this hydrothermal overprint. Now we've got an idea about fluids play a role. And that comes to my most favorite topic about it, is when you look around in the country rocks about hydrothermal alteration. And to my great surprise, you find, I won't say nothing, but very little information or publication or research or anything about hydrothermal activity in this area. But you see plenty actually. So on the right-hand side, so this is original chlorpyroxene gneiss, and they are just shot to pieces with wollastonite veins. And it's not just a vein set, it's actually more like a stockwork. And the other bit within there, within these altered sort of large class of the host rock, you have abundance of scapolite forming. So you have a hydrothermal event being able to fracture these gneisses at 600, 700, 800 degrees. So there's an enormous hydrological pressure. That's on the left side. You see a classic, small but classic one, marble on the left, granite on the right. You have what you would call an endoskarn of garnet and an exoskarn of pyroxene. Very small scale, but I think the next one is a bit bigger. Again, so here is a nice pyroxene gneiss, intruded granite, and 2-3 meters of massive garnetites, garnet skarn. In this case, that's one of our deposits, MS7, and this granite here is mineralized. And in fact, most of the garnets you find near mineralization. If you go further away, you more have wollastonite and scapolite in this area. Now, I'll go a little bit, just go back because we're on the topic. Bear with me here. So we talked about leucogranite, or the local term is alefskite hosted mineralization. And that is true for Ongolo and MS7. Inca itself is not, the mineralization is not hosted in the granites. It's a proper hydrothermal skarn-like, or, you know, it's a hydrothermal mineralization with alteration minerals you would refer to being skarn minerals. So just sort of point it out. The other bit is also, if you go another 20 kilometers to the south here, you come to was originally put out as an iron ore deposit, shale. That is purely magnetite. So it's a magnetite skarn. And there's good reason to think that it forms a system of where you have mostly magmatic hosted, or leucogranite hosted mineralization, to hydrothermal skarn mineralization, to a iron skarn at the bottom end. So you have a system where your fluids over 20, 30 kilometers will separate from its magma and travel up the crust. But just that, I'll go back to my original slide. Now, this is the Rössing formation as it is outcrops. There is a hammer somewhere there. Most of the white strata is marble, and you can see those large lozenges in here, so they're boudins. And these are more siliclastic material. So you can see what enormous amount of strain this unit took up. And by doing that, the marbles, you have this boudinaging effect. And when you look to some reactions of common original minerals to skarn minerals, I'll put the densities of the minerals in here. you tend to see, especially a scar, you forming garnet, you increasing your density, and vice versa, you decreasing your volume of a material. So that is a process that will ultimately create porosity, where you can emplace magmas and fluids into. Oh, I had a so now to Inca. So this is a mineralized piece of core from Inca. All the black in here is magnetite. And then you have these green minerals in here, and they're majorly iron-rich clinopyroxene, Hettenbergite, and iron-rich actinolite. And here in red, that's uraninite. You can see a little bit around here. And through core locking over the years, we could show that uranium mineralization in this deposit is linked to that iron-rich actinolite, which replaces the Hettenbergite and the magnetite. So there's a sequence of alteration minerals, and at the late stage, the magnetite, iron-rich actinolite, that is the uranium event in that case. Any questions? So just to pedal back, so to sum it up, so we think there is no uranium-rich specific melt. What we think happened is the uranium was collated by the fluids in these magmas. They were percolating through this crystal mush, this solidifying liquid granite melt. And because it started to react with these highly reactive rocks in the Ressing Formation, the marbles, which created then an outlet of fluids to be transported away, those fluids then moved within these melts towards that stratigraphic horizon. And the space for it to take place happened to be in those fault hinges. And you go across the deposit. I haven't been to Ressing myself yet, but certainly like Valencia is another deposit. You can see it on any maps or on aerial photo. The mineralized liquid granite sits right in a fault hinge, and that's a pattern that's repeating itself again and again. So yeah, and the key to that is to understand not just the structural emplacement and controls on your aldehydes. You need to understand what within it, how these fluids moved inside. And that's I think, a different view to the established view from before. So thank you.